can appreciate what is the probability to find some change or the other civilization on the Mars?
The probability of finding what?
The traces.
Trace of life. Trace of life on Mars.
No.
Okay, so the question is, what is the probability that we will find the traces of life? I can say that in the past rovers, Sojourner and Mir, the Spirit of Opportunity, the first 3 rovers that we sent, the instruments were much more simple. They mainly had imagers and geologic instruments. But one of the major findings that they found was that there for sure used to be water on Mars. And that's a big deal because as far as we know, all life on Earth requires water. And so that was very exciting. And so that would be, you could say, the first trace of the possibility of life, right? An element of life. Now the Viking landers, which went to Mars back around 1980, they actually did send what were life detection instruments. These were instruments that didn't look for just the traces of life, they actually looked for life itself. And a lot of people ask, well, you know, if life was big enough, if you saw a dog, wouldn't you be able to see with your cameras? And so what I'm saying is that assuming that we don't have aliens walking around and we have little life that might be microbial or life that maybe existed millions of years ago, we're probably not going to find it with a camera, but you actually need very sophisticated instrumentation to determine that there was or wasn't life. And so curiosity does not bring with it a life detection instrument. It brings with it SAM, though, and SAM, the SAM instrument has actually several smaller instruments inside. One of them is a mass spectrometer. It essentially finds the ratio of charge to mass in different molecules, and also a gas chromatograph, which is another way of separating different types of molecules. And together they can actually very precisely tell you what molecules, including organic molecules, you find in a drill sample of a rock or a scoop of soil. And if we, for instance, found what's called organic carbon, or amino acids, or some other molecule that we on Earth know as being essential to life, that would be a very strong trace of life. Now, the probability that we will find that, I don't know. It's hard to say. It's one of the exciting things about doing science somewhere that almost no one has ever seen, and certainly not with this package of instrumentation, is that a lot of things we're going to learn is going to be discovery no matter what, because either way, we don't know the answer. And so it's not just an incremental discovery. When you go to a place that's so new, like Mars, whatever we learn is going to shed light on how we view it as maybe having once hosted life. And that doesn't just go for SAM, but for instance, the RAD and REMS instruments are looking at cosmic and ultraviolet radiation, respectively. And we know that radiation kills life. And so a big part of that is to figure out how far under the soil would life have to be able to survive, given the levels of radiation that we see on the planet. And so as a package, also the DAN instrument that was built in Russia, it looks for water or ice or water locked in minerals, what's called hydrolyzed minerals. And though that also is indicative or kind of rolls into the whole picture of, was there once life? Was it possible there was once life? I think the probability that we will, without any doubt, find life is low, because the rover was not designed to do that. Viking tried to do that, and it was indeterminate. And the reason is because it's very hard to do that. But that said, if there was once life, there's a good probability that it would have left the traces of past life, and that we will be able to see that.
We know that also Phoenix lander mission was searching for water because it was landed to Martian Arctic part. Did the Phoenix found some info about the possibility of sending missions on Mars with humans and sustain some life, or part of generating resources for life?
Okay, so the question is, did Phoenix find signs that maybe we could send humans to Mars?
Yep.
Well, okay, here are two things that Phoenix found. The Phoenix lander, for those that aren't familiar, landed on the Martian Arctic. I worked on Phoenix when I first came to NASA, actually. And Phoenix found water ice on the surface of Mars, which is something we expected. And water ice, of course, can be made into liquid water. But it also found something called perchlorate in the soil. Perchlorate is a chemical or an ion that is used in, for instance, rocket fuel. It's also very poisonous. And so what that tells us is, even at the chemical level, Mars is not easily habitated by human beings. And so did Phoenix tell us that humans can't go there? No. Did it tell us it would be easy to go there and find water? No. But it did give us enough information that we think that given enough study and work and resources, we probably could send humans there. And everything through the Viking landers, through the Viking orbiters, through the rovers that we do today, they all give us information that can help guide future human missions. And that's a big goal of robotic missions, like Curiosity.
Okay, thank you, Anthony. If there are no... do you have a question? Come here. We have another question from public.
Hi, Anthony. I'm Cotiso. I understand that there is no human in Curiosity, and it takes some tens of minutes to communicate, and you only communicate several times per day with the rover. So who's actually driving the rover?
Okay.
The question going further and letting the joke aside is, who is actually driving the rover? What is the computers and what is going on there? I assume that it's a pretty complex system that is taking care not to get into a hole, not to get a flat tire or something like this, and this sort of questions. I believe that some of the young team that we have around here would be interested to understand more about the robotics and the engineering of those robotics that are behind the scene, which are supposed to make it happen, everything else, put up the arm, move it, and so on.
Sure. So the rover is semi-autonomous. That means that sometimes it does things completely on its own, and sometimes it does it carefully as it exactly instructed by operators on the ground. But most often, the rover, when it is semi-autonomous, it is given rough guidelines for what to do, and given what it observes in the environment, or if you're familiar with controls, closing the loop on the environment, it decides what to do to best meet the instructions sent to the rover. And so let's talk about a couple different types of things you might want to do with the rover. The first one, the one I think maybe you're most interested in, is driving. We have rover drivers, or we call them rover planners. And rover planners might be told, we want to drive 100 meters that way to the north to a big rock. And the way that we would do that is the rover planners would have several options. The first thing they could do is they could say, okay, the rover is facing east, the rock is to the north, so I need to turn 90 degrees to the left, then drive 100 meters by spinning the wheels so that I think that I've driven 100 meters. That would be the simplest way to do it, and it's the way that's most prone to error and damage. Because obviously you could drive over a hill or slip on the soil, you don't know what the traction is going to be, there could be a rock in your way that you didn't see from the ground. And so very quickly I think it's obvious to everyone that the rover needs to make some decisions on its own. And so the way that the rover does that is you give it a very high level instruction, which you say, in your local coordinate frame, we set up local coordinate frames, like you might plant flags as you go. We want to go to the rock these coordinates. points, but we want you to decide how to get there. And so the rover has to figure out how to get to that rock, given that it does not yet know the safest route. And so the way that it does that is it does essentially what we do, which is it starts off by taking a lot of pictures. And the pictures are used to build a map in the region around the rover of how drivable different regions of the terrain are. And then it will drive a little, and then it'll take pictures again and map out the terrain again. And it'll drive, take pictures, drive, take pictures. And at the same time, it's tracking things like the motion of the vehicle, the tilt of the vehicle, the odometry on the wheels. It's counting with things called resolvers and encoders. And it combines all that data, and in its mind decides, am I safe, and have I met my objective? And once it thinks it's either gotten close enough to its target, or it thinks it's unsafe, it stops driving. And then it takes pictures, provides what other information are needed by the humans on the ground to know that it succeeded or failed, and then the humans decide what to do next. And so when you do something that's autonomous, the rover does it on its own. If you need a person to be involved in the decision-making process, we call it ground in the loop. And one of the problems with ground in the loop is that it takes a lot longer because we only command the rover once a day. And so if we had to stop, start, stop, start, stop, start, it can take days to get to that rock. Whereas when the rover is autonomous, it can get there in one day. And so figuring out how to make a system of that complexity that is also autonomous, as I think you mentioned in your question, is very difficult. And I know that driving is an obvious one, but there are hundreds of other things the rover has to be able to do autonomously, some of which are very difficult to even think of at the most basic level. And so another example is what happens if an instrument stops working when you're doing a scientific analysis. And so you do something called fault protection, which is you monitor all kinds of values to look for problems. And then when you find a problem, you need to diagnose it and have the rover quickly react, much quicker than a human could react, to protect the instrument or protect the rover. And so we have layers and layers of what's called system and local fault protection that look for problems, and they're called monitors, and then respond, and those are called responses. And the monitors and responses are a large part of the autonomy on the rover meant to keep it safe. And there's autonomy, even when you're driving, it's making sure you don't fall off a cliff, right? If the tilt gets too big, it'll stop you, right? That's part of the fault protection that it does. And so, that said, I don't mean to imply that everything the rover does is autonomous. It's actually very carefully sequenced day to day. And so ultimately when you ask who's driving the rover, the answer is the people on Earth. But they don't always describe it to the T. They give maybe high-level instructions for things like driving that need autonomy. But a lot of things don't need autonomy. A lot of things like taking the weather observations that my instrument REMS does really doesn't require much autonomy except for monitoring the instrument's health and things like that. And so you might just give it a list of instructions called the sequence. And we send dozens to maybe 30, 40 sequences to the rover a day as part of our package that we send the rover in the morning. And it goes through those sequences one by one and executes them. And some of it's very autonomous, some of it's very well directed. And the combination of these two different ways of commanding the rover is what we do every day. And admittedly right now we've done very little autonomous behaviors. Most of what we're doing right now is very cautious and has the ground in the loop for everything we do. But as the rover grows up and we start to trust the rover, we let it do more things on its own, just like you might with a kid.
It seems that you've done a great job there at NASA, preparing the Curiosity rover for every situation. The last question is also from public. Okay.
Thank you. I'm continuing the question with a small one. What are the programming languages that they're using to sense all of these commands that are some of on a higher level, some are like very strict ones? Is it like Microsoft Robotics, or is it something like Lego Mindstorm, or something far more complex?
The rover is primarily programmed in C, and that's what the software on the rover was written in. Now, day to day, we are not writing C programs. Day to day, we are writing sequences, which are text-based lists of commands that we compile into codes that we send to the rover. And that's not a programming language, that's a sequencing language that we created specifically for the rover. And it's essentially a list of recognized commands that the rover knows. And so there's a lot of other programming languages that are used on the ground for ground software. You see things that are written in Python and Java, but most of the software on the rover was written in C. And then the sequences are our own special sequencing language that we use for commanding curiosity.
Thank you, Anthony. I know you're very busy there. Can we take a second last question?
Hi, Anthony. My name is Sorin, and I wanted to ask you with regards to life on Mars, considering the changes that happen in the anatomy of a human body that goes into space, is it viable to think that the human body will adapt if it goes on Mars to the conditions over there?
Well, in some ways, Mars is more like Earth than space, in that there is some gravity. It's about a third the Earth's gravity, whereas in space, in microgravity, there's very little. And so one of the things that I think we've seen with astronauts is they have bone loss from the lack of gravity. We've also found that it's a lot harder for them to do day-to-day activities without any gravity. Where Mars, we do have some gravity, so that makes things a little bit simpler. But that said, you still don't have air, you still don't have water that you can easily harvest as far as we know. You don't have food or plants. And so the biggest biological challenge for humans is getting the nutrients and gases and liquids that we need to stay alive. And some of that we might be able to generate on Mars, but a lot of it we'd have to take with us, at least at the start, until we could maybe build a settlement. So there's a lot of other biological effects that are either hypothesized or have been observed on astronauts, but really we've only sent a couple hundred people into space and not for a very long time. And so the effects of sending someone to Mars, for instance, for a couple years, as has been proposed, really is a big unknown. And a lot of people, including studies in Russia and in the United States, have simulated what would happen just if you put people alone in a base on Mars for that long, and what would happen, and just the psychology of it, which is very challenging.
Okay, thank you very much. Thank you very much once again, Anthony.
You're very welcome.
Finally, before we close, what do you like as a message? What do you like to say to these young people here? Once again, we are here, 400 people from around, especially from Romania, but also from around the world, from 3 continents. I know you. Okay, please.
Well, as a message, I mean, I encourage you all to look at the images and video that we're going to send back from Mars in the next couple weeks and months and years, and also the ones that we sent back in the last couple days since we landed, and think that only 100 years ago, or even 50 years ago, Mars was just another star in the sky. And the idea that we would actually be able to see images from the ground and see how much it looks like Earth, it inspires me to look forward to what it is we'll be able to do in another 50 or 100 years. And what we ultimately will be able to do scientifically and just as a culture really depends on people who are interested in science, math, technology, and are willing to actually dedicate the effort and expertise to accomplish things like this. And so I encourage all of you, if this is exciting to you or amazes you, and it's something you think you might want to do, we won't be able to keep doing it if we don't have people that are willing to learn how to do engineering and learn how to do science. And so if you like it, keep doing it and don't get dissuaded, because ultimately it's very rewarding and very fun. And it's something that hopefully we'll be able to keep making progress on over the years.
Thank you very much. Again, be sure that always in the next period of time when we see and when we hear information from NASA, from Mars, from Curiosity, we remember about you, and we remember that these days we have a chance to speak with special persons which are involved in one of the most important projects of the Earth, Curiosity. Congratulations again, good luck in your work, and all the best for you and your friends.
All right, thank you.
Thank you, Anthony.